Welcome back, AP Statistics. This is part 3 of chapter 15. We're going to talk about what happens when we introduce a constant into a problem involving expectation, variance, and standard deviation. And I'll give you a heads up, this is a concept that College Board traditionally really wants to make sure you know about, okay? There are going to be probably several AP test questions on this topic. So now that you know, let's hop to it. For a random variable x, the expectation, if we were to add or subtract a constant to values the random variable would give us, is equal to the expectation of that random variable plus or minus that constant, right? So if we were to change the values that the random variable would produce by adding or subtracting a constant, the expectation is the same, except we add or subtract that constant. Not terribly difficult to understand. However, would adding or subtracting a constant change the variation? Well, the answer is no. The variation, or the variance, we would say, of a random variable plus or minus a constant is the same as the variation of the random variable, which makes sense. We should not be surprised that adding or subtracting a constant doesn't affect the variation of the data. It just changes where it's centered. This also means that the standard deviation of a random variable plus or minus a constant is the same as the standard deviation. Measures of spread remain the same if we add or subtract a constant to each possible data value we could get, each possible output of the random variable, though the center, the expectation, does change. So let's look at this question again. We've determined that couples dining at Quiet Nook can expect Lucky Lovers discounts averaging $5.83 with a standard deviation of 862. Suppose that for several weeks, the restaurant has also been distributing coupons worth $5 off any one meal, and that is one discount per table, all right, just to keep this problem simple. If every couple dining there on Valentine's Day brings a coupon, what will be the mean and standard deviation of the total discounts they would receive? So, we need to take into account this $5 off any one meal. So we are changing each data value by $5. So we want to see what effect that's going to have on the mean and standard deviation of the discounts that people would receive, or the tables rather would receive. So we're going to let D be the total discount, at least our textbook is, which would be the Lucky Lovers discount plus the coupon. D is equal to X plus 5, X being the Lucky Lovers discount. So the expectation of D would be the expectation of my Lucky Lovers discount plus $5. So we would be saving $5 right off the bat, and then some additional amount because of the Lucky Lovers discount, which is due to chance. So we would say that's equal to the expectation of my Lucky Lovers discount plus $5, which is $5.83 we expect from the Lucky Lovers discount, plus $5 is $10.83. So we can expect on average to be saving $10.83 per table for the Lucky Lovers discount plus this coupon worth $5 off any one meal. The variance is not going to change. It would be the variance of random variable plus 5 is the same as variance of random variable. The spread does not change, which would be 8.62 squared, whatever that is. But the standard deviation would just be 862, same as before. So different mean, same standard deviation. Now on to a different set of rules. For the same random variable x, the expectation of x, except we multiply all the outputs by a, is equal to a times the expectation of the random variable. Again, not too hard to imagine. However, it does start getting a little weird when talking about the variance. The variance of a times x is equal to a squared times the variance of x. And that squared has to do with the fact the variance is the average square distance of possible data values relative to the mean. This means then that the standard deviation of a times x is, now this is a technicality, It is technically the absolute value of a because the square root of a squared is technically the absolute value of a. Also, we don't want a to be negative, then the standard deviation would be negative, which standard deviation cannot be negative. Standard deviation is the average distance of data points relative to the mean. So distance is a scalar, so we need to make sure that this stays positive. So standard deviation of a times x is equal to technically absolute value of a, though for our purposes a is going to be positive, times standard deviation of x. All right, just don't want any angry comments saying, wait, this a needs to be positive. Yep, that's why I put absolute value bars around it, just as a formality. All right, so on Valentine's Day at the Quiet Nook, couples may get a lucky lover's discount averaging $8.53 with a standard deviation of 862. When two couples dine together on a single check, the restaurant doubles the discount offer. That's pretty neat. $40 for the ace of hearts on the first card and $20 on the second, assuming you picked that ace of diamonds first. So, what are the mean and standard deviation of discounts for such groups of 4? All right. Well, we would say the expectation of 2 times the random variable is 2 times the expectation of the random variable. Expectation is 583. 2 times 583 is about 1166. Okay? The variance of 2x is 2 squared times the variance of x. That's equal to 4 times 862 squared, which is almost 300. Now, mind you, we're only supposed to find the standard deviation. You can find the standard deviation via the variance. If you were to find the variance first, you just square root that bad boy and you get 1724, or you could do it directly, which is why I use this formula right here. Standard deviation of a times x is a times the standard deviation of x, assuming a is positive. So standard deviation of 2x is going to be 2 times the standard deviation of x, which is 1724. So we can get our answer directly by saying, okay, here's the formula for variance. That's cool. We derive our formulas for standard deviation via variance. That's one reason why variance is important. But we don't need to use the formula for variance. We can just jump right to the standard deviation, take a 2-step process, and make it a 1-step process. Now we're on to perhaps the most interesting rules of all, the addition rules for expectation, variance, and standard deviation. For 2 independent random variables x and y, the expectation of x plus or minus y is equal to the expectation of x plus or minus the expectation of y. So again, not hard to imagine. What do we expect from a sum or difference of random variables? Well, it's the sum or difference of the expectations themselves. Variance, however, is frighteningly simple. The variance of x plus or minus y is equal to the variance of x plus, no minus. That is not a typo. There's no minus the variance of y. Yes, it is indeed that simple. Now, why is it that simple? Well, when we're talking about expectation, we're talking about data values themselves and the average data value we can expect to see, the average output of a random variable we can expect to see. But regardless of whether we're adding or subtracting random variables, we are introducing 2 different sets of variation, and those different sets of variation compound. That's why there's only a plus sign here, whereas there's a plus or minus over here. Whether or not I add or subtract these random variables should change what my expectation is, but I could add or subtract these random variables, and I am introducing 2 different avenues of variation which compound, all right? So there you have it. Now, the standard deviation is going to be the square root of the variance, which is given above. But when we're told to find the standard deviation of a sum or difference of random variables, we're usually given standard deviations. So what I like to do is say, instead of the variance here, I just write the standard deviation squared plus the standard deviation of the other variable squared, square root that. Then you can just plug and chug right away. By extension, if we have many independent random variables, say x sub 1, x sub 2, x sub 3, so on and so forth, the expectation of a sum of random variables is the sum of the expectations of the random variables. And the variance of a sum of random variables is going to be the sum of the variances. What is true of a sum of 2 is also true of a sum of more than 2 random variables, which means the standard deviation of a sum of more than 2 random variables is the square root of the sum of the squares of the standard deviations of those random variables. These formulas look scary. In practice, they are not that bad. So back to the lucky lovers problems. The Valentine's Day lucky lovers discount for couples averages 583, standard deviation of 862. You probably memorized these numbers at this point. We've seen that if the restaurant doubles the discount offer for 2 couples dining together on a single check, they can expect to save 1066 and a standard deviation of 1724. Some couples decide instead to get separate checks and pool their 2 discounts. So instead of all putting their expenditures on one check, they divide the checks between the couples and then combine their discounts. And the big question is there a difference in that process? So you and your amour go to this restaurant, excuse my French, with another couple and agree to share any benefit from this promotion. Does it matter whether you pay separately or together? Well, let's find out. We need to consider that if we're paying separately, we have 2 random variables in play. Those 2 random variables follow the same rules, but we can't just double the same random variable. We need to consider each check as a distinct random variable. So it's not that we're multiplying a random variable by 2. We are actually working with a sum of random variables because we are summing 2 distinct discounts that follow the same rules, but they are different discounts. So we're going to let x1 and x2 represent the 2 separate discounts. We can't just multiply x by 2. That would be doubling a single discount. We have 2 discounts because there are 2 checks, right? T is going to represent the total. T is equal to x1 plus x2. The expectation for T is going to be the expectation of x1 plus x2, which is the expectation of x1 plus the expectation of x2, which is going to be 583 plus 583 is 1166. Cool. So it really doesn't matter whether we combine the expenditures on one check or whether we split the expenditures between 2 checks in terms of the expectation. However, the standard deviation is going to be different, which is fascinating. So the cards are reshuffled for each couple's turn. The discounts the couples receive are, in fact, independent events. So we have 2 different checks, and the result of one check is not dependent on the result of another check. Why does that matter? Well, let me go back for just a moment. For 2 independent random variables x and y, if the random variables are not independent, none of these rules work. So it's important that we establish independence. Okay? So, if the discounts couples receive are independent, which they are, it's okay to add the variances. The variance of the total savings would be the variance of the sum of the 2 checks savings, which would be the variance of the first plus the variance of the second, which is a different number than we had before by a lot, okay? So the standard deviation of the total savings is $12.19. This is fascinating. So when 2 couples get separate checks, there is less variation in their total discount. The standard deviation is $12.19 compared to $17.24 for couples who pay for the double discount on a single check. It does therefore matter whether they pay separately or together. not in terms of the expectation, but in terms of the variation. So what are we going to do at this point? Well, why not throw another restaurant into the mix? Whatever. The Lucky Lovers discount at the Quiet Nook averages $5.83, standard deviation of $8.62. Ho hum, moving on. Just up the street, the Wise Fool, wise men say only fools rush in, that song. The Wise Fool restaurant has a competing lottery of love promotion. There, a couple can select a specially prepared chocolate from a large bowl to unwrap it and learn the size of their discount. The restaurant's manager says the discounts vary with an average of $10 and a standard deviation of $15. All right. Now, that doesn't mean that you can have negative savings. That just means that there's a lot of variation, probably a high ceiling of savings. So how much more can you expect to save at the Wise Fool? And what is the standard deviation of those savings? So now we're talking about a difference of random variables. So we're talking about how much more can you expect to save at the Wise Fool. So we want to analyze the relationship between, say, W for Wise Fool and X, Quiet Nook. All right, so we want to find the difference between the savings at Wise Fool, which we'll call W, and Quiet Nook, which we'll call X. So we're going to let W be the discount at the Wise Fool, X be the discount at Quiet Nook, and D would be the difference, which would give us the benefit of going to the Wise Fool as opposed to the Quiet Nook. These are different promotions at separate restaurants, so the outcomes are independent. If you do well at one restaurant, it should not affect how well you do at the other restaurant unless there's really a fix going on. So the expectation of the difference in savings would be the difference in the expectations. This is not terribly complicated. So we'd say $10 minus $5.83 is $4.17 approximately. So you're saving on average $4.17 more at the Wise Fool than you would at the Quiet Nook with their Lucky Lovers discount. So the standard deviation, how much variation can we expect differently for W minus X? We could go the variance route. We could say it's the square root of the variance, and the variance of a difference of random variables is the sum of the variances. Again, if we have two random variables in play, it doesn't matter whether we're adding or subtracting, we're introducing new lines of variance. So the variance is going to be the standard deviation for the Wise Fool, which is $15, as you recall. $15 squared plus the variation at the Lucky Lovers discount of Quiet Nook, which would be $8.62, that standard deviation squared, okay? And we square root that, and we get $17.30. Alternatively, we could just cut to the chase and say the standard deviation of W minus X is equal to the square root of the sum of the squares of the two standard deviations that we already know. The first standard deviation is $15, we square that. The second standard deviation is $8.62, and we square that, and we get our answer. Honestly, I prefer this approach in the red better. You decide whether you want to go the variance route with its neat little property of whether we're adding or subtracting random variables. We just sum the variances, and we can square root that, get the standard deviation either way. I like this way. You choose your quest. So discounts of the Wise Fool average $4.17 more than the Quiet Nook with a standard deviation of $17.30. It's a lot of variation, but definitely some good savings here. Definitely would want to go to the Wise Fool as opposed to the Quiet Nook if I were you. So what about those really messy formulas involving like a bajillion random variables I showed you a few slides ago? Well, glad you asked. Suppose we were dealing with the random variable price per person at theme park X. Suppose we were curious about the total price per entry of the next 10 people in line to enter a theme park. Now, people are going to be paying for different rates. Maybe some are paying full day, some paying part day, some paying for just adults, some are paying for adults and children. So all different instances of people coming into the park for different times and different groups of people. So we need to be careful in our calculations. It would not be wise to assume that, okay, we have 10 random variables together. Let's just call it 10 times x. And that's not how random variables work. Since each outcome should be represented by a distinct random variable. It's not just 10 times one random variable. There are 10 distinct random variables. Yes, they're going to follow the same rules, but they're independent of each other and should be regarded as such. It would be more appropriate to represent each person in line as their own random variable. In other words, for example, x1, x2, all the way up to x sub 10. So dealing with many instances, if each instance represents a different outcome for the same random variable, each instance should be written as a different random variable. So if we're analyzing the same random variable 10 times over, we don't just say 10 times x. That would be taking one person and multiplying their result by 10. Now, these are 10 different people. These are 10 different independent events. Even though the random variable is going to follow the same rule each time, we should regard them differently. As we've seen in prior problems, differences in representation do lead to vastly different results, especially when it comes to variation. So let's apply this principle. Suppose the time it takes a customer to get and pay for seats at the ticket window of a baseball park is a random variable with a mean of 100 seconds and a standard deviation of 50 seconds. When you get there, you only find two people in line in front of you, okay? So how long do you expect to wait your turn to get tickets? That's the first one we're going to look at. How long do you expect to wait your turn to get tickets? So what are we going to do for this problem? Well, this word expect should give us a hint. We are going to be trying to find the expectation that for how long it takes for two people to finish the ticket ordering process. So we're going to let x be the time it takes for a customer to get and pay for seats. The expectation of x1 plus x2, these are our two independent customers. They're going to be equal to ex sub 1 plus ex sub 2. And that's equal to 200 seconds, all right? We expect 100 seconds per person, add them together, 200 seconds, easy peasy. Second question, what is the standard deviation of your wait time? All right, now we need to do the standard deviation for a sum of two random variables, which is very different than 2 times the standard deviation. All right, 2 times the standard deviation for one random variable. The standard deviation for a sum of random variables is the square root of the sum of the variances, or squared standard deviations. Standard deviation is going to be 50 each. All right, so that would be 70.7107 approximately seconds, okay? That is very different than the standard deviation of 2 times x, all right? Standard deviation of 2 times x would be 100 seconds, when in reality, since there are two different people in line, the standard deviation is shorter. We're not just taking one person's time waiting to get their tickets processed and doubling it. No, we are considering two different people, so we need to be careful, all right? And part C, what assumption did you make about the two customers in finding the standard deviation? We assume the two customers' wait times were independent events. That's the only way to compute standard deviation for a sum of random variables.